Hello there, and welcome to Dr. XYZ, the what, why, and how of math. Today we are going to talk about something that every student learns very early in school, but very few truly understand: the classification of numbers. Natural numbers, whole numbers, integers, rational numbers. You may remember these names from your school textbooks, but at that age, most students simply memorize the definitions without really understanding why these classifications exist. Because of this, a small gap in understanding begins early and often grows larger as mathematics becomes more advanced. So today, we will revisit this concept from a deeper perspective. Today, we will understand the classification of real numbers and why it plays an important role when solving mathematical equations. Let us begin with a simple algebraic equation. X squared minus 5x plus 6 equals 0. If we plot this equation on a graph, we obtain a parabola. Since the coefficient of x squared is positive, the parabola opens upward. The points where the parabola crosses the x-axis represent the solutions of the equation. Solving the equation gives x equals 2 or x equals 3. Looks simple, just a basic quadratic equation. But there is a small detail in mathematics that we often ignore. Usually the equation comes with a statement like this: x belongs to R, which means x belongs to the set of real numbers. Now pause for a moment and think about this. What exactly are real numbers? Why do we classify numbers into different groups? And how does that classification influence whether an equation or a problem has a solution or not? To understand this, we need to briefly look at how numbers evolved. Numbers did not appear suddenly. They were invented gradually as humans encountered new problems. Imagine a primitive human counting animals. To keep track, he scratches marks on a bone. Each mark represents one object. This is how natural numbers were born: 1, 2, 3, 4. Natural numbers help us count objects. But soon another question appeared. What if there are no objects at all? How do we represent nothing? To express emptiness, humans invented one of the most powerful ideas in mathematics: zero. With zero, the number system expanded into what we call whole numbers: 0, 1, 2, 3. But civilization continued to evolve. Trade began. Money was borrowed and lent. And a new problem appeared. How do we represent debt? Suppose you owe money to a bank in today's context, or you owe your friend 20 euros. That value must be represented somehow. To solve this problem, mathematicians introduced negative numbers. Combining positive numbers, negative numbers, and 0 created a larger set called integers: -3, -2, -1, 0, 1, 2, 3. But mathematics still wasn't complete. Imagine sharing one pizza among 4 friends. Each person receives 1/4. Or imagine splitting a restaurant bill equally. Now we need numbers that represent parts of a whole. This led to the invention of fractions, numbers that can be written as a ratio of 2 integers. These are called rational numbers. Examples include 1/2, 3/4, 7/10. Even decimals like 0.5 or 0.75 are rational numbers. But mathematics soon discovered something surprising. There are numbers that cannot be written as fractions. For example, the square root of 2, or the famous constant, pi, or Euler's number, e. These numbers have decimals that never end and never repeat. They cannot be expressed exactly as fractions. These numbers are called irrational numbers. Now something elegant happens. If we combine natural numbers, whole numbers, integers, rational numbers, and irrational numbers, we obtain the complete set called real numbers. The symbol for this set is R. Every real number corresponds to a point on the number line, from -infinity to +infinity. The real number system is therefore the complete number system used in most mathematics and engineering problems. Now let us return to the equation we saw earlier. X squared minus 5x plus 6 equals 0. The solutions were x equals 2 and x equals 3. These numbers belong to many categories. They are natural numbers, whole numbers, integers, rational numbers, and of course, real numbers. So the solutions fit perfectly inside the real number system. But now consider a slightly different equation. X squared minus 2 equals 0. Solving this equation gives x equals square root of 2. Now here's the interesting part. The square root of 2 is not a natural number. It is not an integer. It is not even a rational number. It is an irrational number. Now imagine we restrict the variable like this. X belongs to the set of natural numbers. In that case, the equation would have no solution of 2. This simple example shows why number classification is important. The set of numbers you allow determines whether a solution exists. So what is the key takeaway? First, the larger the number system you allow, the more solutions become possible. Second, if your number system is restricted, many equations may have no valid solutions. And third, classifying numbers helps mathematicians, scientists, and engineers choose the correct domain for a problem. This idea is used everywhere, in engineering, in physics, in computer science, in finance. Different problems require different types of numbers. So the next time you see an equation with an unknown like x, ask yourself an important question. What kind of number can x be? A natural number? A rational number? An irrational number? Or any real number? The answer can completely change the solution of the equation. Let us summarize. Real numbers include all numbers that can be represented on a number line. They consist of both rational and irrational numbers. And classifying numbers helps us understand where solutions to equations can exist. Thank you for watching Dr. XYZ and staying till the end. If you enjoyed this explanation of real numbers and their classification, consider liking the video and subscribing to the channel. Every subscriber is an added integer for my channel. Here we explore the what, why, and how of mathematics. If you have questions, or topics you would like to see in future videos, write them in the comments.